Hello, my name is Behrad Farzinfar. I'm a PhD student in environmental engineering at Clarkson University, and I'll be presenting my poster titled Enhanced PFOA defluorination using an integrated plasma UV hydrogen peroxide process at the 4th Annual Healthy Water Solutions meeting. So let me quickly share my slides with you so I can give you a quick rundown of what I'll be presenting in the meeting. PFAS, or the so-called forever chemicals, are one of the major environmental issues in the modern world. They have contaminated our water resources worldwide, and they're called forever chemicals because they're very persistent to natural degradation processes. There's almost no processes that can break them down in the nature. And the reason for their persistency is the strong carbon-fluorine bonds in their structures. However, plasma have proved to be an efficient process for degrading these compounds. We produce plasma by applying a very high voltage between two electrodes. In this case, we have a needle high voltage electrode over the water surface and a ring ground electrode submerged in the solution. Our working gas is argon, and we have worked on removing PFOA, which is a major long-chain PFAS compound that has been extensively used. So when the discharge forms, plasma produces a lot of reactive species that diffuse into water and start reacting with the organic compounds within a few nanometers from water surface. However, despite effective PFOA degradation, plasma alone is not able to achieve full mineralization. That means in the treated solution, there still remains some fluorinated organic compounds that are not our parent PFAS, but are still organic compounds are not desirable. So you can see that in the graph on the right-hand side, that PFOA is degraded within 20 to 30 minutes from the start of the experiment, but fluoride yield plateaus at around 50%, almost half of the experiment. Fluoride yield is an indicator of mineralization and shows how much of the initial fluorine atoms in the parent PFOA is released in its inorganic form. And in the diagram on the left-hand side, you can see there are multiple pathways with which plasma can degrade PFOA. Some are desired pathways that lead to complete defluorination, but some are undesired that lead to production of some intermediates that plasma is not able to further break them down. And that's the bottleneck and the reason for incomplete mineralization. So our solution and our hypothesis was that if we can integrate the plasma process with another process to produce OH radicals or some other kind of reactive species in the bulk solution, we can target these compounds and achieve higher defluorination. And that actually worked. So here are the key results. You see that the integrated process successfully improved defluorination from 50% to around 80%, which is a major improvement. However, we did not achieve full mineralization in 2 hours of treatment. But the good news was that the trend of fluoride yield did not plateau as it did in the case of plasma alone. So we extended the treatment to 4 hours, and we achieved around 96% fluoride yield this time, which we called near complete defluorination. The remaining 4% of fluorine was accounted for in the remaining very short chain byproducts that plasma were not able to effectively break them down. So the take-home message here is that plasma alone degrades PFAS but falls short of full mineralization. We showed that coupling plasma with UV hydrogen peroxide drives deeper defluorination by producing OH radicals in the bulk solution. However, the integrated process also increased the remaining ultra-short chain compounds in the treated solution, which will be the focus of our future research to remove these compounds from the treated solution. So thanks for listening to me, and I hope to see you at the meeting.